everyone, and welcome to this explainer. Okay, think about this. Every single hour, the sun hits the Earth with enough energy to literally power our entire planet for a full year. Today, we're going on this absolutely incredible journey to see exactly how we capture that energy. We're going to trace the path from a microscopic singular photon traveling across the vacuum of space, all the way to the massive, pulsating utility grid that powers our modern world. It's this amazing story of quantum mechanics meeting macro electrical engineering, and the crazy part? It's happening silently on rooftops everywhere. So, here's the core question that's going to guide our whole exploration today. How does a tiny particle of light actually end up powering your home? I mean, really think about that for a second. We aren't burning anything, we aren't spinning some massive turbine with steam or water. We're taking raw ambient sunlight and transforming it into usable, highly reliable electricity. How on earth is that invisible transformation actually achieved? Well, to answer that, here is our roadmap for today. Number 1, the photovoltaic effect. 2, inside the PN Junction. 3, tracking maximum power. 4, inverting DC to AC. And 5, synchronizing with the grid. Let's kick things off with our very first act. Section 1, the photovoltaic effect, the quantum spark. We're zooming way down to the atomic level here to understand exactly where this journey begins. It all starts with the photovoltaic effect. By definition, this is the creation of a voltage, or a corresponding electric current, in a material upon exposure to light. But just shining light on something isn't enough to make power. The light has to trigger a very specific electrical response within the material itself. We need a way to harness that light, physically break atomic bonds, and force the resulting energy to flow in a single, useful direction. And that directional flow brings us right to Section 2, inside the PN Junction, semiconductor mechanics. This is where the physical separation of electrical charges actually happens. Okay, let's really dive into this. To make a solar cell work, engineers essentially sandwich two different types of altered silicon together. On one side, we have an N-type semiconductor. You can kind of think of the N-type side as a crowded room with extra people. Those are our negatively charged free electrons, and they're all looking for a seat. Now on the other side, we have a P-type semiconductor. Think of this side as a room full of empty chairs, which we call mobile holes, and these essentially act like positive charges. By bringing these two radically different chemical environments together, we set the absolute perfect stage for a massive electrical imbalance. Now, right at the boundary line where these two sides meet, something wild happens. Because of that imbalance we just created, those extra electrons naturally want to rush over to the empty chairs on the P side, and the holes want to diffuse over to the N side. But as they cross over, they leave behind these fixed ion cores that can't move. This creates a charged zone called the depletion region. And what's absolutely crucial here is that this separation of fixed charges creates a really strong, built-in internal electric field right at the junction. So what happens when sunlight actually hits this setup? Well, when incident photons strike the semiconductor, if they have enough energy to cross what's called the material's band gap, think of it like an energy toll booth, they excite an electron. This breaks the electron free from its bond and creates what we call an electron-hole pair. Because this happens right in or near that built-in electric field we just talked about, the field immediately sweeps the electron in one direction and the hole in the other. And boom, just like that, we have a continuous flow of direct current, or DC power. But producing DC power is really only half the battle. Now we're moving on to Section 3, tracking maximum power, extracting the max. We have to pivot away from the physics of creating the power to the engineering challenge of optimizing it, simply because the real world is constantly changing. Enter maximum power point tracking, or MPPT. Listen, this isn't just some passive, static component. Think of it as the active, super intelligent brain of the solar system. It's a highly sophisticated algorithm built right into modern inverters that's constantly hunting. It's making tiny adjustments in fractions of a second to ensure the solar panels are always operating at the exact voltage and current combination that yields the absolute peak power output. And it seriously has to be intelligent. MPPT must dynamically adapt to shifting variables all day long. We're talking about a passing cloud abruptly changing the solar irradiance, a hot afternoon shifting the silicon's voltage, or even fluctuating electrical load requirements. If the system couldn't adapt to these real-world variables in milliseconds, well, a huge amount of potential energy would just be completely lost. So the crucial point here is this. Utilizing this dynamic MPPT technology results in a massive 10 to 30% increase in overall energy yield compared to older static systems. To put that into perspective, for an average residential setup, that could mean an extra 500 to 1,500 kilowatt hours of pure clean energy extracted every single year, just by having a smarter algorithm on board. It's a total game changer. All right, now we're transitioning to the macro level with Section 4, Inverting DC to AC, the great conversion. We've got our fully optimized direct current power. But your house and the massive electrical grid outside your window, they don't use DC. They speak a completely different electrical language, alternating current, or AC. Let's look at exactly how the inverter translates that power. It literally chops up that flat, continuous DC line. First, the internal controller compares a high-frequency triangular carrier wave against a mathematically perfect low-frequency sine wave. By doing this comparison, it generates a rapid series of electrical pulses whose widths perfectly mimic the shape of the desired AC wave. Finally, it pushes these harsh, choppy pulses through an output filter, which is basically an electrical sponge, and that smooths it all out into a beautiful, high-quality AC sine wave with minimal harmonic distortion. Which brings us to Section 5, Synchronizing with the Grid, the perfect rhythm. Now we have to execute the final and undoubtedly the most delicate stage of our journey, merging our newly created pristine AC power with a massive utility grid safely. Precision is absolutely mandatory here. You see, the power grid is like a massive, thumping heartbeat. Our synthesized AC waveform must perfectly align with the grid's voltage, its frequency, and its exact phase. A mismatch here? That would cause incredibly destructive circulating currents. In fact, if the grid suddenly loses power, the inverter has to instantly detect this and sever the connection. This critical safety feature is called anti-isolating, and it ensures your solar panels don't accidentally electrocute utility workers who are trying to fix a downed line. To ensure this perfect rhythm, the inverter relies on something called the phase-locked loop, or PLL. Think of the PLL as the master conductor of the whole operation. It's a foundational electronic circuit that literally never sleeps. It continuously monitors the grid voltage at the point of common coupling, tracking its frequency and phase with intense mathematical precision. Let's break down how it actually pulls this off. The architecture of a PLL relies on three main internal blocks working in a constant, relentless feedback loop. First, you have the phase detector, which essentially acts like an ear listening carefully to the grid. Then you have the loop filter, which cleans up that signal, kind of like a funnel. And finally, the oscillator, which acts like a metronome setting the internal rhythm of the inverter itself. By constantly comparing the phase of the grid against its own output, the PLL generates a tiny little error signal. The inverter takes that error signal and uses it to instantly adjust its internal oscillator, minimizing the difference down to zero. It literally forces the solar inverter to lock onto the grid's exact phase in real time. This amazing feedback loop is what enables stable synchronization, allowing your system to seamlessly inject real, usable power into your home while keeping the entire local grid perfectly balanced. From a tiny photon striking a silicon atom, breaking a bond, and generating an electron-hole pair, all the way up to complex algorithms forcing mathematical harmony with a continental power grid, it is truly astounding, isn't it? So I'm going to leave you with this thought. As our reliance on renewable energy deepens, how will these invisible quantum mechanics and lightning-fast grid synchronizations continue to transform the future of our global power infrastructure? The silent physics happening on rooftops everywhere is really just the beginning. Thank you so much for joining me for this explainer, and keep learning.